Thank you all for joining us for today's Tools and Resources webinar on the PFAS Innovative Treatment Team, also known as the PITT, and the findings of the PITT on PFAS Destruction Technologies. This presentation will highlight the results of the PITT's research and next steps for PFAS waste treatment technologies. If you have a related science question during or after the presentation, please type it into the Q&A window at any time. And once the presentation ends, we will go through as many questions as time allows. You can listen through your computer speakers. EPA plans to post today's PowerPoint presentation on our website within the next week, and the recording will be posted within 2 weeks. At this point, I'll turn it over to Tim Watkins. Tim is the director of EPA ORD's Center for Environmental Measurement and Modeling, and he will introduce the PITT topic and our presenter. Tim?
Thank you very much, Lisa, and welcome everybody. It's a pleasure to be able to present this information to everyone. So I think, as everyone is aware, the treatment of PFAS-contaminated waste or media is one of the most significant problems facing the Environmental Protection Agency, both within our program and regional offices, as well as our partners and customers in our state and local organizations, as well as our federal partners and industry as well. And given the urgency of that need of understanding the efficacy of various treatment and disposal or destruction options for PFAS, our office within EPA, the Office of Research and Development, decided to apply a new approach for us that was based off of a concept that we learned about from NASA called a Skunk Works project, where you basically bring together a group of individuals from multiple disciplines and ask them to focus on a single problem. And so that's something that a new approach for us within the Office of Research and Development. And moving forward with that, we chose Dr. Brian Gullet to lead that effort, the first effort in the Office of Research and Development. And I'm happy to introduce Brian now to provide you guys with a summary of the findings from the PITT, as well as our next steps and path forward. So with that, I will turn it over to Brian.
Thank you, Tim, and thank you, Lisa. I appreciate that introduction. So it's my pleasure to present this talk to you about the PITT on the PFAS Innovative Treatment Team on PFAS Destruction Technologies. And the presence of these per and perfluoroalkyl substances in the environment is probably one of the most pressing environmental issues facing our nation, in my opinion. And this is because they have unique chemical characteristics, they're persistent in their environment, and their complete destruction is extremely difficult. I've worked over 20 years in the field of chlorinated dioxins and furans, and in my opinion, this is a much more intractable solution or issue that we need to address just due to the number of compounds, the complexity, the breadth of the issue. So to make sure we're all on the right webinar, I want to talk a little bit about per and polyfluoroalkyl substances. These are a large class of synthetic chemicals. They're all man-made. They consist of carbon chains surrounded by fluorine atoms, and they have different terminal ends that present different properties, chemical properties. And there are thousands of these, thousands of variations of these chemicals. The last I heard, there were some 9,000 different variants. They are widely used in industrial processes and consumer products, and they have properties make them quite mobile in air, water pathways. The molecules are constructed of a head group, a carboxylate, which is actually hydrophilic, but the tail group which is comprised of fluorine atoms, is actually hydrophobic and hence nonpolar. And hence these are interesting surfactant chemicals. Now, there's been a number of health effects that have been identified associated with these these chemicals in the environment, and these include kidney cancer, testicular cancer, ulcerative colitis, thyroid disease, high cholesterol, and pregnancy-induced hypertension. In fact, a past colleague of mine, Dr. Linda Birnbaum, gave a lecture last Friday as part of the UNC, University of North Carolina School of Public Health last Friday, and she's a former division director at the EPA Office of Research and Development and former head of the National Institute of Environmental Health Sciences. This is an excellent lecture if you want to hear more about the health effects of PFAS chemicals. So PFAS, PFOS, is actually a fabric protector that was manufactured by 3M. It's commonly known by Scotchgard. It's also a C8 compound like PFOA, and they both have hydrophilic tails and hydrophobic/lipophilic ends. Some of these chemicals have been used historically in aqueous film forming foam, which is a fire suppressant widely used by the Department of Defense to put out fires. It's also been used by fire departments and airports. So let me present a brief outline of what we're going to go through this afternoon, and I'm going to talk about the PITT a little bit, elaborate a little bit on what Tim mentioned, talk about our goals, some of the challenges we faced. I'm going to talk about technologies, both combustion and non-combustion technologies, and going to talk about our outputs from the PITT and some of the next steps that we're going to be going through. And you can follow along with this outline by just looking at the key at the footer of each slide. As Tim mentioned, the PFAS Innovative Treatment Team, or PITT, was a full-time team comprised of multiple disciplines of EPA scientists, including chemists and engineers and toxicologists. And we worked for a focused effort of 6 months, starting around March and ending at the end of September of this year, or of last year. And we were focused on a single problem, and that was how to remove, destroy, and test PFAS-contaminated media and waste. So in doing this, we worked to understand current and emerging destruction technologies that were under research by not only EPA, but also universities, other research organizations, and industry. And we're trying to understand how well these method works in destroying the original compounds, but also in how they avoided creating new environmental hazards by simply transferring compounds to a different media or transforming the chemical properties of the PFAS compounds without actually destroying them and mineralizing them. And we also wanted to look at each method's feasibility, their performance, to validate potential solutions. So the PITT's goals were to develop a toolbox of solutions for the destruction of PFAS in media and contaminated waste. And our focus here was on trying to meet the needs of the EPA program offices, as well as the regions, the states, federal agencies, and industry. And as I mentioned, we looked at more traditional technologies, which are typically combustive or incineration technologies, and tried to look at the temperature and time conditions for breaking the carbon-fluorine bond. We also wanted to look at performance of flue gas cleaning systems and analyze for potential byproducts. We also put a significant amount of effort into looking at innovative or so-called high risk, only because they're relatively new, non-traditional approaches for destroying PFAS, and also looking at their byproducts. And the end goal of this, of course, was to try to understand how well these technologies destroyed the PFAS in these wastes, but helping people to make better decisions regarding waste disposal, end-of-life issues, et cetera. And the latter was particularly true in light of the National Defense Authorization Act, which basically commissioned EPA to look at combustive technologies for destruction of PFAS waste. The sources we considered were 5. We basically looked at biosolids or sludge, which is an end product of wastewater treatment. It's a liquidy, but also solid type material that has to be treated, and it may also contain PFAS in it. Some traditional solutions include land application, but in situations where there's high concentrations of PFAS, that can lead to some problems, some concerns. We looked at contaminated soils that were contaminated with the application of aqueous film-forming foam or those fire retardants. We looked at the AFFF concentrate itself, as well as the spent AFFF, that is the material that's been applied as a fire retardant. We looked at combustors, so we looked at waste issues, landfills and landfill leachate, because of the numerous consumer products that contain PFAS. We also looked at a lot of water treatment technologies that ended up with activated carbon, spent activated carbon, and anion exchange resins. Of course, as everybody knows, there were considerable challenges, and COVID-19 was quite considerably limiting in our 6-month stint on the PITT. This, of course, led to building closures, laboratory closures, restricted access of people to our labs, to fix equipment. Suppliers were closed, and lots of times if instruments needed repair, we could not repair them. We also had other limitations in terms of trying to understand how well technologies work, particularly the ones that are existing, such as combustion technologies. And this was difficult because we were having a hard time finding field partners that were willing to participate with us to allow EPA on site to do sampling to understand the potential destruction of PFAS compounds in those systems. And we also had a scientific challenge. This is an interesting situation because the science of sampling for these thousands of compounds, as well as the chemistry of analyzing for them, is actually developing concurrently with our effort to understand how to destroy these compounds in the environment. So this was an interesting challenge as we try to do both at the same time. Now let's jump into the innovative technologies we looked at. There were 4 innovative technologies that we looked at, and the first is mechanochemical treatment. This is a really interesting technology. Basically, it's a ball mill treatment, and you can see a schematic of a ball mill down in the bottom left of the slide. Basically, what you do is you introduce dry solids or semi-dry solids into a ball mill. This is a rotating device that contains a lot of heavy metallic balls that crash into each other, and they fracture the solids, and they generate these very localized high temperatures and create radicals that react and break down organic molecules. And lots of times this treatment technology is used with co-milling reagents, as you can see in the second dot point. This technology has been used in the past to treat persistent organic pollutants, including polychlorinated biphenyls and other compounds. So for this work, what we did is we actually went into 2 phases. We did an in-house laboratory effort, which is ongoing, and we also contracted with a firm that is probably pretty well advanced in terms of the technology, and that's called EDL. They're in New Zealand, and they did a study where they looked at AFFF impacted soil and found up to 99% destruction of the targeted PFAS. There's more work that's ongoing in this effort. We are continuing to look at what the potential byproducts were, and we hope to have some reports out on this later on in this year. The next technology we looked at is called electrochemical oxidation or electrochemical treatment. This technology defluorinates and mineralizes both short and long chain PFAS compounds through a reduction oxidation reactions using a proprietary electrode. It can be a portable technology. It can operate in batch or continuous mode. We actually entered into an agreement with AECOM, which is a tech company that has developed this technology. And what you see here is a picture of some of their bench scale apparatus that we worked on with them to test. The left side apparatus is a control system, and the right-hand side is actually the reactor. This was the pilot scale system. They're constructing a smaller unit in Australia at this time. So this technology has a potential to destroy PFAS, but there are some questions that need to be resolved and that it needs to be optimized for each waste stream. So the kinetics of the reaction are really a function of the electrode characteristics such as surface area, power, material, etc. It's also a function of the co-contaminants and the PFAS concentration. And there's also questions about volatiles that may be generated, and the EPA is also looking into this. So we are expecting more results from this in May of 21, and hope to have a more comprehensive evaluation of the performance of this technology. The next technology we looked at is called supercritical water oxidation, and this is a process that occurs at high temperatures and pressures for generally liquids, and these temperatures and pressures are above the mixture's thermodynamic critical point, and for water this is 374 degrees Celsius and 221 bars. And under these conditions, the fluid becomes very unique. It has unique properties. The fluid has a density between that of water vapor and liquid, and exhibits a really high, almost gas-like diffusion rates, which enhances collision and reaction. And the water actually becomes more like a solvent. So the property of the water is altered. It becomes much less like a polar solvent, and so is able to dissolve organics that are in the waste. And it also tends to cause any salts that are in the feed to precipitate out, and which can be treated by other methods. This is an interesting technology which has actually decades of development behind it, and is just now being applied to PFAS-related wastes. We're doing some work related to SQO in-house and on a hydrothermal oxidation reactor. We also had 4 different vendors whom we worked with to demonstrate this technology. A Danish firm called Aquarden, Battelle and their Annihilator technology. We also worked with a technology based out of Duke University and a spin-off called 374 Water, and also General Atomics. We're working with them to demonstrate this technology also. This next slide shows some of the pictures of SQO apparatus. The Battelle system on the left, the Danish system in Aquarden, which is actually a pilot scale unit. The 374 Water unit is actually at Duke University. It's a relatively good sized pilot scale unit, and then the General Atomics unit on the right. These companies were testing dilute AFFF and basically trying to increase their concentration of the AFFF that they were treating to try to improve the process. Some of these technologies also have pretreatment technologies such as reverse osmosis or even hydrothermal oxidation, which tends to be a pretreatment step prior to SQO itself. The last waste type for PFAS that we looked at, and I mentioned this before, was biosolids. And we looked at technologies of pyrolysis and gasification. These are both technologies that use limited or oxygen-free environments and elevated temperatures to destroy the compound, the organic compounds. It's not really a combustion system, but it's basically a high temperature semi-oxidation reaction, gasification reaction. And we actually did a test with a firm called Bioforce Tech out in California, and monitored their input biosolids for PFAS, the scrubber water, the biochar. And we also had a multi-position FTIR instrument which measured the potential production of hydrogen fluoride as a byproduct for the PFAS destruction. And we also looked at combustion technologies such as incineration. And this technology is defined as basically destruction or mineralization of the chemicals using heat. And the heat is applied directly to the PFAS contaminated waste, whether they be solids or sometimes even liquids. If there are any vaporized combustion products, they can be captured by traditional gas control technologies such as precipitation or wet scrubbing. It's one of the few technologies that has been most demonstrated to potentially destroy PFAS. It has destroyed a lot of similar halogenated chemicals. However, questions do remain regarding the products of incomplete combustion, the stack gas analysis, and other factors. And for this work, for combustion technologies, we did work both at the EPA laboratories and also at the University of Dayton Research Institute. The University of Dayton Research Institute, or UDRI, has traditionally done a lot of work with combustive incineration, including halogenated chemicals, so they were an ideal partner for this effort. Both of these sites, both at EPA, Office of Research and Development, and UDRI, were looking at temperature and time effects, injecting known solutions into different heated flame environments and looking at byproducts. And also, UDRI looked at the destruction of granular activated carbon or ion exchange resins. And these tests on this scale were sort of precursors to field sampling efforts at facilities with different combustion processes, which we pursued throughout the 6-month term of the PITT. But as I mentioned before, we were not successful at gaining access to any of these sites at this time. And we hope that that will change soon. Testing at UDRI seemed to be supported by work at EPA, in which in-flame studies, say greater than 1,000 degrees Celsius or 2 seconds, destroyed the initial PFAS compounds. However, like all the other technologies I've just mentioned, the byproducts have not yet been fully analyzed, and so the long-term efficacy of the technology still has to be assessed. The PITT also developed a guide on waste technology applicability and design considerations. This is going to be put into a paper form in the next few months. What we did here is we looked at the 4 non-combustion technologies and their application to these different wastes. The 5 wastes are listed here, and this is sort of an excerpt. The slide and the next one are an excerpt of what's going to be in the paper. We looked at the different wastes. We characterized how the wastes be formed, and also looked at the scale issues. We combined those waste related issues with the technology related issues in terms of selection of treatment and management of the process, and just tried to articulate all the factors involved in making decisions on how to dispose of certain types of wastes with these 4 innovative technologies. And I want to mention for sure that these technologies were not the only ones that we considered. We considered a whole bunch of them, but in the limited time that the PITT had available, we felt that these were 4 technologies that we could most appropriately advance in terms of their development. So this is not to rule out anything else or to say that these technologies are necessarily the best. It's just that we felt with our limited resources and time that we could probably make a good effort at moving these towards an understanding of how well they functioned. So this introductory paper that I mentioned, we'll talk about technology readiness. We actually looked at the crosswalk, the 4 innovative technologies with the 5 waste types, and came up with this matrix. The team came up with this matrix and the basis for their decisions in terms of ranking the technologies in terms of their applicability to the waste, their technology readiness level, and the key for the technology readiness level is shown in the upper right-hand corner. The PITT also produced 4 research briefs on these 4 innovative technologies, and these are about 2 pages long each, and you can see them at the website indicated on the top right. This gives you sort of an introduction to what each of these technologies are, how they work, and their current level of development. It also talks about the research gaps and some potential for removal efficiency. So I encourage you to take a look at them if you're interested in these 4 technologies. The PITT also developed a challenge as a part of challenge.gov, and this was a fun effort in which we're trying to look at and find solutions for non-novel, alternative, non-incineration technologies that offered a path towards destroying AFFF compounds, which is a significant problem for the Department of Defense, and as well as airports and fire departments. So the goal then was to destroy this compound while not creating any hazardous byproducts. And there's an award effort awarded for the winner of that technology. We partnered with many different partners, agencies, and we appreciate their efforts. The Department of Defense, ECOS, Colorado Department of Public Health and the Environment, and Michigan Department of the Environment to put forth this challenge. So this is the timeline of the challenge. It was launched on August 25th to some fanfare. The past administrator, Andrew Wheeler, announced it, and the winner is scheduled to be announced this month in February. We had 212 people that were interested in presenting a solution. We had 64 submissions from 18 countries. And after the judges went through the submissions, 23 of the solutions, the solvers, met the minimum acceptable criteria and were then ranked for their ability to destroy AFFF. So in summary, we have conducted over the past 6 months, ending in September 30th, laboratory and pilot scale work, both at EPA and universities and industries throughout the globe. And we've looked at destruction of initial PFAS compounds. We found up to 99% loss with virtually all the technologies, with the caveat, of course, that significant research still needs to be made to understand what exactly these initial compounds transformed into. As many of you know, sometimes the compounds that you look for in chemistry are the only ones that you find, and if you're not looking for something that you don't think is there, sometimes you don't see it. So we still have to assess the overall efficacy of these technologies, whether they be combustion, SQO, pyrolysis, electrochemical oxidation, or mechanochemical treatment. And so we hope to do that. We hope to do that over the next year or so. So this concludes my talk, or sorry, next steps. I must have skipped a slide here. So as I said, we hope to continue this work over the next year or so, identifying the byproducts that are formed during these treatment processes. We're trying to explore opportunities for field sampling with industry and other federal agencies, as well as looking at not only the combustion technologies, but also these innovative technologies. And we hope also that the winner of the challenge gets to a next step in terms of its development of its technology. In doing these next steps, we have already achieved funding from the Department of Defense to examine thermal stability of PFAS, and this is a proposal with EPA and University of Dayton Research Institute. We are continuing the SQO work. We have proposals into the Department of Defense, and we're also continuing the electrochemical oxidation work and the mechanochemical work. Well, this concludes my talk, and I appreciate your tolerance of if you have any questions, as Lisa indicated in the beginning, you can type them in. I am Brian Gullet. I'm the lead for the PFAS Innovative Treatment Team, and my director is Tim Watkins.